Hello students, welcome to this second lecture on least squares estimators. Let us recall the general linear model considered for LS estimation is given by x vector is equal to A matrix multiplied by theta vector plus E vector, E is the error vector, where x is the data vector comprising of x1, x2 up to xn, A is a matrix comprising these elements which are known. We assume that E is a white vector. The matrix A is assumed to be a full rank matrix. In other words, the columns of A are linearly independent. Suppose this column, and like this we can get the column, and these columns are linearly independent. We know that LS estimators use sum square error as the cost function, and SSE is given by j theta, that is equal to x vector minus A matrix into theta vector whole transpose into x vector minus A times theta vector. Okay. And we can expand this cost function like this. And also we minimize this SSE cost function with respect to theta, and resulting is the normal equation given by A transpose A times theta LS hat is equal to A transpose x. So, this is the normal equation for LS estimation, and the LS estimator is given by theta LS hat is equal to A transpose A whole inverse into A transpose x, and this we denote by pseudo inverse of A into x. Therefore, theta hat LS is equal to pseudo inverse of A into x. In this lecture, we will discuss the LS estimation of signals. So, earlier we discussed about LS estimators of parameters. Now, we will be estimating signal using the LS principle, and we will also discuss some statistical properties of LS estimators. First we will see linear least squares estimation of signals. Suppose S is the signal vector comprising of S1, S2 up to Sn. Then the linear model of S is given by S vector equal to A times theta vector, that is equal to theta 1 times A1 vector plus theta 2 times A2 vectors plus up to theta k times AK vectors. So, we denote the columns of A by vectors. Suppose this is my A1 vector, this one is A2 vector, like that this is AK vector. So, this column is A1 vector, this column is A2 vector, this column is AK vector. Therefore, S vector is equal to summation theta I AI, I going from 1 to k. The observed data are given by, that is the observation x is equal to S signal plus error, that is equal to A times theta plus error vector. Now, the cost function of least squares approximation is given by j theta, that is equal to x vector minus A times theta vector whole transpose into x vector minus A times theta vector, and this we can write as norm square of x minus A theta. So, this is the notation for norm. Here it is Euclidean norm, Euclidean norm, Euclidean norm. So, this is norm square. So, we have to minimize this cost function with respect to theta i's, and upon minimization with respect to is theta j, we get this is suppose for the square term we will get this, and then it will be a transpose, because this norm can be written as x minus a theta transpose into x minus a theta. So, that way we will get this term transpose of this term into, and when we take the partial derivative of this expression with respect to theta j, we will get a j. So, what we get that x minus summation theta I ls hat into a I going from 1 to k whole transpose into a j is equal to 0. And this is nothing but the least square estimation error, which we denote by ELS hat. Therefore, ELS hat transpose into a j must be equal to 0 for j is equal to 1, 2 up to k. So, least square estimation error is orthogonal to each of the column vectors a 1 up to a k. So, this condition that ELS hat transpose a j equal to 0 for j is equal to 1, 2 up to k are known as the orthogonality conditions. So, error is orthogonal to each of the column vector. Now, from the orthogonality conditions we can get the normal equations. So, this is my equation orthogonality condition. After a little algebra on this set of equations, we get the normal equations. Again, suppose because this is true for j is equal to 1, 2 up to k, and all these equations can be represented into this normal equation given by A transpose A into theta ls hat is equal to A transpose x. So, from this, as we have done earlier, we can find out theta ls hat, and the estimated signal vector will be given by s ls hat, that is equal to A times theta ls hat, and that is equal to A times A transpose A inverse into A transpose x. So, this is the least square estimators of the signal S. We will consider one example. Suppose the observation xi I is equal to 1, 2 are related by xi is equal to theta 1 plus I theta 2 plus ei, that is equal to Si plus ei. There is a signal component and this is the error component. Then x vector will be comprising of x1 and x2. A matrix will be given by 1, 1, that is first row, 1, 2, that is the second row. So, this is the A matrix. Therefore, A1 vector will be 1, 1, A2 vector will be 1, 2. So, applying the orthogonality conditions, we can get that is signal x1 x2 minus theta 1 ls hat times 1, 1 minus theta 2 ls hat times 1, 2 whole transpose into 1, 1, that is first basis vector will be equal to 0. Similarly, the same error times the second column vector, that is 1, 2, that must be also equal to 0. So, we get a set of two linear equations by applying the orthogonality condition and solving the above linear equations. We can get theta 1 ls hat and theta 2 ls hat. We can interpret least squares estimation as orthogonal projection. We have the orthogonality conditions. ELS hat transpose AJ is equal to 0 for j is equal to 1, 2 up to k. Now, estimated signal is given by this SLS hat is equal to summation theta ILS hat times AI, I going from 1 to k. So, this is the estimated signal. Therefore, ELS hat transpose times S hat LS is equal to ELS hat transpose into summation theta ILS hat into AI, I going from 1 to k. So, we can write this inner product like this, and we can take summation outside and then we will get this expression. What we note that this quantity is equal to 0. ELS hat transpose AI is equal to 0. The estimation error, this is the estimation error vector, is orthogonal to the least square estimation. Therefore, the estimation error, that is ELS hat, is orthogonal to the LS estimator, that is SLS hat. So, error vector is orthogonal to the estimator. Therefore, the LS estimator can be considered as the projection of the data vector on the signal subspace spanned by the columns of A. Because this error is orthogonal to the estimate, therefore, what we can do is that we can consider that this LS estimator is a projection of data vector to the space spanned by the columns of A. For example, this is a two-dimensional space spanned by A1 and A2. So, we have this space spanned by A1 and A2. So, suppose this is the space. Now, x is the vector, this is the vector, data vector. So, we project x to this space, if we call this space as S2, then we project x to S2 such that this error part is orthogonal to this estimate. So, this is the error and error is orthogonal to this estimate. So, this is the estimation. This we obtain by projecting x on this subspace. So, in that manner, LS estimator can be interpreted as projection of the data vector to the subspace spanned by the columns of A matrix. We have SLS hat, that is the least square estimator of the signal, equal to A transpose A inverse into A transpose x. This is the least square estimation, and denoting this part by P matrix, we get that least square estimator is equal to P times x. This matrix P is equal to A transpose A inverse into A transpose is known as the projection matrix. It is a projection matrix which has some interesting properties. We will not discuss about these properties. Therefore, we can get the least square estimators by multiplying the data vector by the projection matrix. Now, let us discuss the statistical properties of LS estimator. First property is theta LS hat is unbiased. We have theta LS hat is equal to A transpose A whole inverse into A transpose x, and we will substitute x is equal to A theta plus E. Therefore, theta ls hat is equal to A transpose A whole inverse into A transpose into A theta plus E vector. Now, we will take the expectation E of theta ls hat will be equal to, this part is constant. So, we can take expectation inside E of theta plus E of E, and theta is a deterministic parameter. So, this will be theta and this will be equal to 0. So, what we will have, E of theta ls hat is equal to this term plus into theta, but we see that here this is inverse and here the matrix A transpose into A. Therefore, this part will give identity matrix. Therefore, we will have only theta. Therefore, E ls theta hat is equal to theta. So, theta ls hat is unbiased. So, this is a very good property. It is one of the desired properties of estimators. We have established that theta ls hat is unbiased. We will examine if theta ls hat satisfies the minimum variance property, because for a good estimator the variance should be as low as possible. For this, we will find the covariance matrix of theta ls hat. Consider the observation model x is equal to A theta plus E, where E is a white noise vector. So, samples of white noise are uncorrelated and they have the same variance sigma square. Then the covariance matrix of theta ls hat is given by C theta ls hat, this is the notation, is equal to sigma square times pseudo inverse of A into pseudo inverse of A transpose, and that is equal to sigma square times A transpose A whole inverse. So, this is the expression for the covariance matrix of ls estimator. C theta ls hat is equal to sigma square times pseudo inverse of A into pseudo inverse of A transpose, which is also equal to sigma square times A transpose A whole inverse. We will prove this. C of theta ls hat is equal to E of theta ls hat minus theta, because it is unbiased, into theta ls hat minus theta transpose. This is the definition of covariance matrix. Now, this we can write in terms of theta ls hat is equal to pseudo inverse of A times data vector. So, pseudo inverse of A into x minus theta into pseudo inverse of A into x minus theta whole transpose. So, this is the definition for C theta ls hat, and now we will write x is equal to A theta plus E. Here also x is equal to A theta plus E. So, A plus pseudo inverse of A into A, we will get identity matrix. Similarly, here also we will get identity matrix. Pseudo inverse of A into A is identity matrix. Therefore, theta and this theta will get cancelled. Here also theta and this theta will get cancelled. What we will have is E of pseudo inverse of A into E transpose into pseudo inverse of A transpose. So, covariance matrix of theta ls hat will be given by this. Now, we know that expected value of E transpose is a diagonal matrix sigma square I. I is the identity matrix. Therefore, what we will have is, that is, this covariance matrix will be equal to sigma square times pseudo inverse of A into pseudo inverse of A transpose. And if we expand this pseudo inverse and pseudo inverse transpose, we will get this expression. because pseudo inverse of A is A transpose A whole inverse into A transpose, and here whole thing transpose. And if we carry out the algebra, we will get this term A transpose A into A transpose A inverse, that will become identity matrix. Therefore, what we will have is sigma square times A transpose A whole inverse. So, this is the covariance matrix of LS estimator. So, covariance matrix of theta hat LS is given by this expression. Thus, we have proved that C theta LS hat is equal to sigma square times pseudo inverse of A into pseudo inverse of A transpose, and which is equal to sigma square times A transpose A whole inverse. So, this is the covariance matrix. Therefore, the diagonal elements of C theta LS hat will give the variance of each component of theta LS hat. So, we know how to get the variance of the LS estimator. Now, to prove the minimum variance property, we consider another unbiased linear estimator theta tilde is equal to dx. This is another unbiased estimator, so that the variance of this estimator will be bigger than variance of theta LS hat. So, to prove this, we need another theorem. If theta tilde equal dx is an unbiased linear estimator of theta in the model x is equal to A times theta plus E vector, then D matrix into A matrix must be identity matrix. How we can prove this? We have a very simple proof. We have E of theta tilde is equal to theta, because theta tilde is an unbiased estimator. Also, E of theta tilde is equal to E of dx, because theta tilde is equal to dx, and that is equal to E of d times x is equal to A theta plus E. Therefore, E of d times A theta plus E, that is equal to dA theta. So, E of theta tilde is equal to dA theta, and E of theta tilde is equal to theta. Therefore, dA theta must be equal to theta, which implies that dA must be equal to identity matrix. So, if there is any unbiased linear estimator theta tilde equal to d times x, it must satisfy this identity. D times A is equal to I. I is the identity matrix. Now, we will prove this theorem. Suppose the observations are given by the model x is equal to A theta plus E vector, where the measurement error vector is white. This is important, is white noise vector. Then theta LS hat is the best linear unbiased estimator of theta, because we are considering only class of linear and unbiased estimator. Out of that class, theta LS hat will have the least variance. Theta LS hat will have the minimum variance. We will prove this. Covariance matrix of theta tilde is equal to E of theta tilde minus theta into theta tilde minus theta transpose, which is equal to E of, now theta tilde is equal to E of theta tilde is equal to dx minus theta into theta tilde is equal to dx minus theta whole transpose. So, this is the covariance matrix. Now, we will write x is equal to A theta plus E. Therefore, C theta tilde is equal to E of d times A theta plus E minus theta into D times A theta plus E minus theta whole transpose. So, covariance matrix can be written like this. And we note that D into A must be equal to identity matrix. Therefore, wherever D into A comes, we will get the identity matrix, and because of that D into A into theta will be equal to simply theta. So, this theta and this theta will get cancelled. Similarly, this side also D into A will be identity matrix, therefore, this theta and this theta will get cancelled. Therefore, this expression will be equal to E of D times E transpose into D transpose, because D times E transpose will be E transpose into D transpose. Okay. Now, we know that expected value of E transpose is the diagonal matrix with diagonal elements sigma square. Therefore, this expression will be simply equal to sigma square times D transpose. In other words, the covariance matrix of theta tilde vector is sigma square times D transpose. Now, the diagonal elements of this covariance matrix will give the variance of the linear estimators of the individual parameters. So, diagonal elements of C theta tilde will give the variances. We have to minimize the diagonal terms of D transpose to find the best linear estimator. So, our problem is to minimize the diagonal terms of D transpose. Using the relation dA equal to I identity matrix and some matrix algebra, we can show that D transpose is equal to pseudo inverse of A into pseudo inverse of A transpose plus this expression D minus A that is pseudo inverse into D minus pseudo inverse transpose. So, if you carry out algebra using dA is equal to I, you can easily prove that this left hand side and right hand side are equal. Now, this is a matrix and its transpose, therefore, this will be a positive semi definite matrix into matrix transpose, therefore, this part will be a positive semi definite matrix. Now, the diagonal elements of D transpose will be equal to diagonal elements of pseudo inverse of A into pseudo inverse of A transpose plus diagonal elements of this matrix. Therefore, diagonal of D transpose is minimized whenever those of the diagonal of this matrix is minimized, because this is a fixed matrix. Therefore, diagonal elements of D transpose is this diagonal of this fixed matrix plus diagonal of this matrix, which we must minimize. Okay. And we know that this matrix is a positive semi definite matrix, therefore, its diagonal elements are non-negative, and smallest value of the diagonal elements will be obtained if we put D is equal to pseudo inverse of A. In that case, D minus A plus this quantity will be equal to 0, therefore, this diagonal element will be equal to 0. Okay. Therefore, this expression will be minimized whenever we put that D is equal to pseudo inverse of A. Okay. The variance will be minimum if that linear estimator is equal to pseudo inverse of A itself. Therefore, theta LS hat is equal to pseudo inverse of A into x has the lowest variance. So, it will have the lowest variance among all unbiased estimator. Okay. Therefore, least square estimator theta ls hat is the best linear unbiased estimator when the measurement error vector E is white. This is important. Only when E is white, least square estimator is blue, best linear unbiased estimator. What is the blue for theta when the measurement error vector E in x is equal to a theta plus E is not white? So, what will happen if E is not white? For that, the answer is the Gauss-Markov theorem. We will prove this theorem. Suppose the observations are given by the model x is equal to a theta plus E, where the measurement error vector E is 0 mean, like in the previous case, with the covariance matrix C. Earlier covariance matrix was a diagonal matrix with constant diagonal element, but here we have a general covariance matrix. Then the blue of theta is given by theta blue hat. This is the base linear unbiased estimator is equal to A transpose C inverse into A whole inverse into A transpose C inverse into x vector. So, this is the expression for base linear unbiased estimator for any parameter theta. Now, if we put C is equal to diagonal matrix with constant diagonal element, then here we will get this will be sigma square into A transpose A inverse. We will prove this theorem by the whitening approach. We have taken the whitening approach in the case of IIR causal Wiener filter. You remember that. Similarly, here also we will prove this result by whitening the error vector. We will prove this result by whitening this error vector. Because this error vector is non-white, we will use a transform to make it white. Since this C inverse matrix is positive, definite, real and symmetric, it can be factored as C inverse is equal to L transpose, where L is an invertible matrix. This is known as the Cholesky decomposition. This is in fact it is a lower triangular matrix and this will be an upper triangular matrix. Further, E of L transpose E into L transpose E transpose, that is equal to L transpose, and then E will take inside E transpose into L, and this E transpose is equal to C. Therefore, this expression will be L transpose into C into L, but C is equal to L transpose inverse, because we have assumed that C inverse is equal to L transpose. Therefore, this will be C will be equal to L transpose inverse. So, we can write this expression equal to L transpose into L transpose inverse into L, and this inverse will be L transpose inverse into L inverse. Okay. So, what we get is that this side is L transpose inverse into L inverse L, and this expression will be equal to identity matrix. So, L transpose inverse into L inverse into L will be the identity matrix. Thus, L transpose can act as a whitening transformation on E. So, what we have seen is that the transformation L transpose into E is white. Now, let us consider the model x is equal to a theta plus E. Therefore, L transpose x will be equal to L transpose A theta into L transpose E, where L transpose E is white. Therefore, in this case we can get the best linear unbiased estimator, because if we consider this as the data, this is the linear model and this is the error. L transpose E is the error. So, this error is white, therefore, we can find out the best linear unbiased estimator, which is the least square estimators for this data. And therefore, this best linear unbiased estimator will be equal to the least square solution of this problem, that is equal to L transpose A whole transpose into L transpose A whole inverse into A transpose L transpose X, because instead of A matrix now we have this matrix. So, we have to find out the pseudo inverse of this expression, which is given by this. And now we note that L into L transpose is equal to C inverse. So, what we will get is A transpose C inverse into A whole inverse into A transpose C inverse into X. Okay. So, this is the base linear unbiased estimator when the error is non-white with covariance matrix C. Now, let us see what is the mean and variance of this estimator. So, E of theta hat blue will be equal to this is a constant times Ex. Now, Ex is x is equal to A theta plus E, therefore, this term will be equal to simply theta, because E of E is equal to 0. So, we will be having all these terms and we see that this part is inverse of this part. So, that way this will be simply equal to theta. Therefore, theta hat blue is an unbiased estimator. And similarly, we can find out the covariance matrix of this theta hat blue, and this is equal to E of theta blue hat minus theta into theta blue hat minus theta transpose, and we will substitute now for theta blue hat, this expression will substitute. This is the expression we get here. So, that we are substituting here, and we will carry out the algebra. So, we are substituting theta blue hat. So, we can carry out the algebra and we can prove that C theta blue hat is equal to A transpose C inverse A whole inverse. So, this is the covariance matrix for theta blue hat. So, base linear estimator of theta will have this covariance matrix. The diagonal terms of C theta blue hat will give the minimum variances of the components of theta blue hat. So, what will be the minimum variance, that we can find out from the diagonal elements of this matrix. Let us consider one example. Consider the problem of measuring a DC quantity A in presence of the measurement error xn is equal to A plus En, where En is a 0 mean with variance sigma n square. Find the blue for A. Comparing with the linear model x is equal to A theta plus E, we have theta is equal to A, and A matrix will be simply 1 1 1 transpose, and covariance matrix will be given by this, because sigma n square is the variance. Therefore, we can apply the formula for blue. So, this will be given by this expression, which is equal to this. Okay. Let us summarize the lecture. In LS estimation, the signal S is modeled as S is equal to A theta, which is equal to theta 1 times A1 vector plus theta 2 times A2 vectors plus up to theta k times AK vectors, which is equal to summation theta I I going from 1 to k. LS principle is applied to estimate S from the noisy observation x is equal to S plus E, which is equal to A theta plus E. The normal equations can be obtained by applying the orthogonality principle, that is ELS hat transpose times A j vector is equal to 0 for j is equal to 1, 2 up to k. The LS estimator of the signal is given by S LS hat is equal to A times theta LS hat, which is equal to A into A transpose A whole inverse into A transpose x. The LS estimator is the projection of x on the signal subspace spanned by the columns of A. We have also proved that theta LS hat is an unbiased estimator. Then the covariance matrix of theta LS hat is given by C theta LS hat is equal to sigma square times pseudo inverse of A into pseudo inverse of A transpose, that is equal to sigma square times A transpose A whole inverse. For any unbiased linear estimator, theta tilde is equal to dx, we will have dA is equal to I. D into A matrix, D matrix into A matrix will be identity matrix, and the covariance matrix of theta tilde is given by sigma square times D transpose. When the error vector is white, theta LS hat is the best linear unbiased estimator. When the measurement error vector is 0 mean with the covariance matrix C, then the blue of theta is given by, this is the theta blue hat is equal to A transpose C inverse into A whole inverse A transpose C inverse into x. So, this is the best linear unbiased estimator when the error is non-white with covariance matrix C. Thank you.